All right. Yep. Great. Okay, so welcome everybody, and today we have the great pleasure to have Giovanni Ceribella.
Thank you.
Giovanni, well, a little bit about his scientific life. Giovanni started doing a master's at the University of Padova, already in the magic collaboration. And afterwards, they decided to move to Germany, to the Max Planck for physics, to do his PhD. And then he traveled a bit far away to Tokyo at the ICRR for his first postdoc, and now he's currently at the Max Planck for physics in Munich as a postdoc.
Yeah.
And Giovanni has been, he's been working on the MAGIC and LST and CTAO collaborations for around 10 years or so. He's been doing a lot of technical work as technical coordinator of MAGIC, but also he's been involved on the study of pulsars since his master's thesis, I think. And today he will talk to us about extreme pulsars and also what CTAO has to say about them. So please.
Yeah, thank you, Ruben. You make me seem much more important than I am. Yeah, but okay, so hello everybody. Ruben already introduced the topic. I will be talking about gamma ray pulsars. Thank you all for having me here today. Yeah. I was asked to give a brief introduction about pulsar physics, so I will just go quickly over some of the basic concepts, and then essentially I will present what the status of the research is in this respect with pulsars with Cherenkov telescopes. So it's very high energy emission from these objects in an energy range between few tens of giga electron volt and actually few tens of tera electron volts. Yeah. Okay, so pulsars. This is the Istituto di Astrofisica, so I suppose I don't need to explain you what neutron stars are. Yeah, so compact objects with very, very large magnetic fields spinning very fast due to the momentum conservation. Yeah. Also very small, and many of them emit radiation in the form of pulsars. Here you can see one rare image, one rare video of the optical emission of the crab pulsar. They were named so because they seem to be pulsating. Yeah. The periods are generally very short. It was understood quickly that this pulsation is due to the rotation of the star. So between few milliseconds and even up to several seconds, I think this is actually a bit outdated. The most recent ones is several tens of seconds, the slowest ones. Yeah. This is non-thermal emission. Yeah. And if you look at a typical profile, this is what we will see later, this plot again. You see an impulse, then some quiescent state, then another impulse, and so on and so forth. Yeah. So this phase here from 0 to 1, in this case, it is around 30 milliseconds. Yeah. Usually these objects are categorized in this diagram that has the period of the pulsation on one axis and the derivative of the period on the other one. Yeah? These objects slow down with increase in time generally. Yeah? So it basically represents an analogous of the Hertzsprung-Russell diagram for these objects. There are various classes. In here, you can see in light blue the ones that emit anything that is more energetic than radio. Yeah, most of these objects are detected in radio. However, some of them, particularly in this sector of the diagram here, but also surprisingly down here, emit high energy emission. So they can be visible in optical, not many of them. In fact, in X-rays, there's a lot of them, and there's also gamma rays. Yeah. So it is commonly understood that youngest pulsars are born in this region of the diagram, yeah, and then they migrate downwards here. What happens here is that if they have a companion, if they are in a binary system, they might get spun up again by accreting material, so they can go back to very low period, and they become, in this case, what are known as millisecond pulsars in this area. Yeah. Okay, very briefly, these are a few slides that come from a previous lectures I gave. How do these things work? Yeah, I should say what I'm talking about here mostly are the so-called rotation power pulsars. Yeah, so I already mentioned that they might be in a binary system. If so, they can accrete material, and then we can see the pulsations where the source of power is the accretion of the material. What I'm talking about today is instead pulsars in which it is the rotation itself that powers the phenomenon. These are very highly magnetized objects, but in our understanding, they are also excellent conductors, even superconducting, apparently, superfluid and superconducting in the nucleus of these objects. So one can simply view these as a sort of dynamo and calculate what the electric field and the force felt on particles on the surface of the neutron star would be compared to the gravity, and it can be easily shown that it is many orders of magnitude larger. So the particles, if there is any charge on the surface of the pulsar of the neutron star, it would be ripped out from the surface and it fills a vast region surrounding the neutron star. In fact, if the neutron star was in a vacuum here, you can see the distribution of how the potentials would look like. This case with a pulsar in a vacuum is analogous to what you have if you take a generator, and you don't active, so it's powered, but you don't connect it to anything. A very powerful generator that is not connected to anything. It will build up charges, and as soon as it can, there will be a spark. It will short circuit, and it will create a lightning. Yeah. So this is essentially what happens. Charges are extracted from the neutron star, and they build up in this fancy way, in such a way, in fact, that the magnetic field lines of the neutron star become electric equipotentials. So in that stage, it's kind of the equilibrium is kind of reached. Yeah. This enormous mass of plasma that surrounds the neutron star is what constitutes the pulsar magnetosphere. And it has been understood in the decades following the discovery of neutron stars that it is in this magnetosphere that we have phenomena, the phenomena that cause the pulsed emission. Yeah. I should briefly mention, because it will be relevant later, that it's not that all the particles are extracted from the pulsar. You can just extract one particle. It will be accelerated to incredibly high energies due to synchrocurvature radiation. It will radiate gamma rays. Now, this process here in normal conditions, it's prohibited. It doesn't exist in quantum field theory because it violates the conservation of momentum. But in the humongous magnetic field of the neutron star, we are talking about 10 to the 8 Tesla. The magnetic field, which is in fact also made of photons because it's electromagnetic interactions absorbs the missing momentum that is missing from this energy, from this reaction. So any gamma that is promptly produced close to the neutron star in this enormous magnetic fields produce a cascade of further particles, mainly electrons and positrons. And so in fact, this mechanism makes the magnetosphere full of this leptonic plasma of positrons and electrons, and this is the origin of the plasma that we observe there. Yeah. Briefly, don't look at the formulas; they are not useful at all. Yeah. We have this plasma field magnetosphere. It can be proved that close to the neutron star it is co-rotating. So if the pulsar rotates at an angular velocity, at an angular frequency of 10 hertz, the entire magnetosphere also rotates at 10 hertz. But there is a limit. The limit is the speed of light, yeah, because the particles by magnetohydrodynamics requirements, in this case in almost ideal conditions, are bound to these magnetic field lines. They are sort of frozen in the magnetic field. If the magnetic field with the pulsar is rotating at such high angular frequencies, there is a limit which is where the rotation would reach, the co-rotation would reach the speed of light. There clearly the particles cannot co-rotate anymore with the neutron star. So there the geometry and the character itself, the nature of the magnetic fields change abruptly. What happens is that if you have magnetic field lines that cross this surface, this limit surface, the light cylinder, they physically cannot close back and come back to the neutron star. They can do so much later when the plasma is no more ideal. In fact, they merge with the intergalactic, interstellar and intergalactic as well magnetic field. So the system satisfies the usual requirements for magnetic field. The divergence is zero. There are no magnetic monopoles and all those things. But what happens is that these lines, in fact, leave the neutron star forever. And if you have particles from that leptonic plasma in the magnetosphere that are following and happen to be on these magnetic field lines, they will stream away to essentially infinity and leave the neutron stars. So the neutron star creates a pulsar wind, which is a wind made of electrons and positrons that leave the neutron star and dissipate in the surrounding medium. Yeah. I think this is possibly the most striking, the existence of this light cylinder limit and of this wind is possibly the most striking fact about pulsar magnetosphere. Yeah. This wind makes the pulsar lose energy because it's streaming away things. So again, in a circuit analogy, you have a generator. The closed part of the magnetosphere is an ideal plasma. There is almost no power loss, but then we have this enormous resistance, which is the wind. So most of the energy that the pulsar dissipates goes into this particle wind. What we see as electromagnetic radiation is due to defects in this wind, where the ideality of the plasma is not really satisfied, and when we have a conversion to electromagnetic energy via one mechanism or another. In fact, it's still an active research topic. Yeah. I should briefly mention also that all of this that I said is true even if the magnetic field is perfectly aligned with the rotation axis. Yeah, you don't really need the magnetic field to be tilted for the dynamo effect. It would be called the homopolar generator if it is aligned. But yeah, it doesn't need to. You don't need to have the tilt for it to work. Yeah. Okay, so I mentioned that we have this ideal plasma. If it was ideal everywhere and perfect, we wouldn't have any acceleration of particles, because I told you before that these magnetic field lines are also electric equipotential. It means that the electric field is always perpendicular to the magnetic field. If the particle needs to move along the magnetic field, it can never feel an electric field, so it can never accelerate. So this means that there are somewhere, actually this picture, it's outdated now because we know there's even another, no more newer class of models. Somewhere in the magnetosphere and in the surrounding of the neutron star, there must be a place where this ideality is broken. So originally, it was supposed that this was very close to the neutron star, close to the polar cap. This PC is polar cap. But what happens there is that since there the magnetic field is extremely strong, this process that I mentioned earlier of single photon couple production would reabsorb any gamma ray that can be produced there. So later people start considering a possibility that somewhere you have a gap in the plasma where you can feel. So if there is no plasma, the field configuration changes and you can feel this electric field. So they hypothesized that there was a gap along this last closed field line. This dashed line would be the limit surface, the light cylinder, or in this area here. I believe that nowadays I'm not really sure if these hypotheses have been abandoned completely, but I think they certainly do not have much support as in the past. Here I added another region, which is this equatorial current sheet. It is just beyond the light cylinder. If you do the math, you see that the pulsar is losing charges from the poles, but the pulsar needs to, the neutron star needs to be keep neutral all together. Otherwise, it would start attracting things from the cosmos. Yeah, so there is a return current that goes through the equator. Some models show that there might be there a site for acceleration. In any case, even the simplest case, which is the one in which you have the magnetic field and the rotation axis perfectly aligned, and in which you neglect any other force acting on the plasma, including gravity, even that one is not analytically solvable. The first solution was from, I believe, 1999, when computers became more readily available. Yeah. So I've put here a couple plots from recent papers just to show that it is in fact quite complicated. Here you see different cases with the inclination of the magnetic field with respect to the rotation axis. Here the colors are proportional to the divergence of the electric field, so essentially they are proportional to charge. And you see this return current here around the equator, which is the current sheet. If the pulsar is tilted, it becomes much more complicated. It becomes very complicated. Now I added this picture of the current sheet viewed from meridian plane, yeah, and from the equatorial, it kind of goes in a spiral, but it also does a structure like this. When I'm talking to friends trying to explain this, I always make the example that is like if you took a tissue of velvet, yeah, and you started doing this game, it would do more or less something like that. It is a bit difficult to visualize, but if you are familiar at all with solar physics or heliophysics, there's a structure which is very similar to this in the solar wind. Yeah. once the particles are accelerated and we don't know exactly where and how they are accelerated, they can radiate gamma rays or more in general radiation via the synchrotron and curvature or more generally the two together synchrocurvature emission. Yeah. These are often treated in astrophysics in the context of cooling times, yeah, of the electrons. The difference between the two types is really minor. It's just that in synchrotron, the electrons, the particles, the charged particles are spinning around the magnetic field lines, whereas in curvature emission, they are forced to follow them. So the dependence on the gamma factor, essentially the energy, the Lorentz factor of the electron changes. It is more pronounced for curvature emission. Yeah. A nice fact about this is that if you have a population of electrons, I'm continuously talking of electrons, but I mean this is general for any type of particle, yeah, that follows a distribution according to a power law. The resulting spectra will also be power laws with the index linked to the power law of the particles. Yeah, there can also be inverse Compton emission. And here you need to be careful because if you are talking about gamma rays, the energy of the photons that are produced are much larger than the rest mass of the electrons. So compared to the formula that you usually find in textbooks, we are in another regime of the interaction, which is the Klein-Mishina regime. So the exponents here, the relation changes. But here, the numbers and the formulas don't really matter. What matters is that you can have a relation between the spectra and the properties of the emitting particle. Yeah. So far for the introduction. I understand it was a bit heavy. So if you have one or question, we can do it now before going on. No, everything was crystal clear.
What I understood is that we don't know exactly where these electrons are accelerated, but we know at least. I mean, we don't know even if the emission, the gamma ray emission is. I mean, it should be inverse Compton or this.
We really don't know. We really don't know. So.
I think it is better if we keep the questions till.
Yeah, but it's just to go quickly. So
Yeah, we'll cut you for.
Fine.
Anyway,
so you see,
you want to use,
one possible site of acceleration is supported by some numerical simulations is around here, where you have this junction between this current sheet and the closed magnetosphere. And there, essentially, they postulate that you can have in those conditions a very strong electric field that is parallel to the magnetic field, and then it can accelerate particles, like if you would do in a linear accelerator. Yeah. The other possibility is that in this complicated structure of the current sheet, you might have a reconnection in the plasma, yeah? And then you could accelerate the particles there. Whether then the gamma ray emission comes from synchrocurvature from inverse Compton, at the usual energies that we observe these objects, the gamma ray pulsars, which I will show you in a moment around the GeV, the emission is quite well understood to be synchrocurvature. Yeah? But at the highest energies, the one that we can probe with Cherenkov telescopes, we have evidence in at least two cases, the Crab pulsar and Vela, that we have inverse Compton emission as well. Okay, I move on. So, gamma ray astronomy, very briefly, because I think many people here are familiar with it. Yeah. So we are talking about observing gamma rays from the cosmos. So this is pretty much all non-thermal emission. We have a bunch of detectors to do that. One of the most successful experiments and telescopes of the recent decades was the Fermi-LAT detector, yeah, observing from few tens of mega electron volt up to possibly beyond, if the source is very bright, 100 giga electron volt. We have a Cherenkov telescopes here. I've put magic as a example, yeah, that cover from few tens of giga electron volt up to 100 tera electron volt. If we go to even higher energies, we have these extensive air shower arrays like here. There's Hawk or LASO, which is the newest arrival and is kind of revolutionizing the field. Yeah. Why can't we go to these highest energies with something like Fermi-LAT? Simply because the fluxes are super low and you need to launch the thing on board of a rocket, so you can make it so very large, and then it cannot have enough effective area collection area to probe these energies. Yeah. So concentrating on imaging atmospheric Cherenkov telescopes, which is what I will show you about. These are the current, or say already getting older experiments. We have Veritas in Arizona, we have Hess in Namibia, we have a representative here as Emma, and we have Magic in Spain, actually, in La Palma. Yeah? So these observe between, I said, few tens of GeV and few tens of tera electron volt, or even hundreds. And just, I won't get in detail to the detection techniques, but just for the sake of being clear, these are these telescopes record events. So each single photon is recorded, and then we derive the spectra and the science from the statistical ensemble. It is similar to what is done in X-rays. Yeah, so we have single photon. There are also some single photon optical photometers out there. Yeah. So an event looks something like this. This is actually not a gamma. This is certainly a cosmic ray, because this arc can be very easily identified. It was a muon that was produced in the atmosphere. Yeah. Anyhow, event by event, then all the bunch of events are grouped, and statistics is used to infer the properties of the source. Yeah. But we have also newer instruments, yeah. So the CTAO, the Cherenkov Telescope Array Observatory, is arriving to town. This is the render of how the site will look. It will be in La Palma, yeah. Once it is completed. This is really a huge project that put together all the people from the field, yeah. And it will have different sizes of telescopes so that it better covers different science cases. No, larger telescopes for the lower energies to collect more light from the dimmer showers, smaller telescopes, medium-sized telescope with a larger field of view, yeah, to cover better highest energies and galactic sources and so on. Yeah. It will also be an observatory as opposed to the current experiment. So people will be able to apply for time and get it as happens commonly in astronomy elsewhere. Yeah. And yeah, I should say that it is not really in the future. The prototype of the LST telescope here is already in La Palma since several years. This photo is from last summer. Now I can tell you that the mirrors here, they were installed but covered. In this one have been uncovered. Mirrors have been installed in this one as well. They are building it. The expected first light for this LST4, which is this one, is essentially now. So we are getting into the array. Okay. Again, back on gamma ray pulsars. And how much time do I have? 10, 15 minutes. Should be fine, should be fine. If not, you can you can cut me, yeah. So we know nowadays we know hundreds of gamma ray pulsars, yeah. We used 20 years ago to know 10 of them, yeah. But with the launch of the Fermi-LAT telescope, we now know hundreds of them, mostly in this band here, reaching around 10 GeV, because that's where the synchrocurvature emission is expected to die out. But it kind of, the situation is still the same, but it kind of moved to highest energies. No, we have 5 that are seen above 50 GeV. And as I was mentioning, there is no consensus yet on the emission details. What accelerates the particles? What is emitting the gamma rays? The dynamics and structure of the magnetosphere of these objects is not understood. Why some of these 5 emit up to 100 GeV essentially, whereas all the others don't. It is kind of a field in its infancy here, yeah. Here there is kind of a historical overview about the results. I can skip through it. Just mention that already in 2008, before Fermi-LAT results came, this polar cap model that I mentioned earlier was already ruled out because the Crab pulsar was detected by magic at around 25 GeV. I mentioned this very strong magnetic field close to the neutron star. If the emission came from there, it would absorb the gamma rays efficiently at energies of around 10 GeV with a cutoff in the spectrum that is stronger than an exponential. So you wouldn't see anything. Anyhow, it was kind of a competition and a run between Magic, Hess, and Veritas. I can go through here. I will just present you now the 3 that we know best about, which are the Crab pulsar, the Vela pulsar, and Geminga. Yeah. The Crab really doesn't need much of an introduction. There's the current joke that when one, what do you do? I'm an astronomer. Do you are an astronomer that works on Crab or one that doesn't? Yeah, so it's a famous, a very famous object. Yeah, roughly 1,000-year-old. The total spin down luminosity. This is the power that is emitted by the pulsar, mostly in the form of wind, is 10 to the 5th times the solar luminosity. Yeah, very strong magnetic field. It is the power source for the pulsar for the Crab nebula. So what do we see when we go and have a look in gamma rays at the Crab pulsar? This comes from Magic. You see there is here a quiescent phase that we actually use to estimate the background. And you have 2 pronounced peaks. The relative intensity of these pulses changes with the energy. This is also an interesting phenomenon. And then here it's almost invisible, but if you compare the average level between the 2 pulses with the one in the quiescent phase, you can see that there is still some emission between them. This is called the bridge emission. Also, just to make it clear, the two pulses are not separated by 180 degrees. Yeah. In the lighthouse model that one has in mind, the two pulses come from the 2 beams that are at the opposite side. So one would expect them to be 180 degrees apart. But in reality, it depends completely on the viewing geometry. And then the pulsar is not really a lighthouse. Yeah. So the emission doesn't need to be 180 degrees. The 2 pulses don't need to be 180 degrees apart. In fact, there might even be more than 2 pulses. Yeah. If we have a look at the spectra of these 2, so these are the recent results from the LST. We see here at the lowest energies this sort of large, relatively flat emission. This is the one for the P1 and P2. They are different, yeah. This is the synchro curvature component that is seen by Fermi-LAT. And then going on at the highest energies, this transitions into a power law tail that really isn't compatible with the prosecution of the synchro curvature model. And this is actually interpreted as coming from inverse Compton. However, if one would postulate that this is a synchro curvature and this is inverse Compton, we would expect to see some break in between when the two components pass from one to the other. In fact, we don't see anything. It's a very smooth, continuous prosecution. Yeah? That reaches up in the case of P2 tera electron volt energies. I should mention quickly that I mentioned briefly the bridge. There is emission also in between, and there is actually structure in between, yeah, that is presently not explained. So you have a strong emission. You can imagine this as viewing this SEDs, this spectral energy distribution from the top. So I have phase on the x-axis, energy on the y, and you're seeing the spectrum from the top. Yeah? So you see that it varies quite a lot within, and all of these things depend on the specific emission scenario that you consider and on the viewing geometry. Yeah? For instance, the one that I mentioned before with this equatorial current sheet, it predicts the relative intensities of the pulses. P1, the first one, decreases with energy, which is what we observe, but it fails at predicting the bridge emission. Yeah. So in here, since we have so few objects, it's really we really can't tell yet what's the difference between the models and if one is preferred over the other. Okay, now I'm talking about the Vela. For the Vela, I took a few slides from the excellent presentation by Emma of last week at TEVPA. All credit to Emma for the slides. If I make any mistake, all of those are on me, yeah, not on her. Yeah. The Vela is also a very energetic young pulsar, but it is 10 times closer than Crab, roughly. Yeah? So it appears in the GeV regime of Fermi-LAT as the brightest point-like object of the sky. Yeah? And the Hess telescopes, they detected emission below 100 GeV and down to 10 GeV already. I think it was 2015 when it was announced. Yeah, and they also see something that can be modeled as a power law, but it is superimposed here on the model coming from Fermi-LAT of the synchro curvature emission. Yeah, so it is kind of interpreted as a prosecution of the synchro curvature emission, but then surprise, has also detected emission way beyond the tera electron volt scale, yeah, reaching up, in fact, it is this azure, this blue area here, this blue butterfly reaching up to 20 and more tera electron volt. So in the case of Vela, that you can compare here to the Crab pulsar, we see something different. In case of Crab, it is the synchro curvature emission transitioning question mark into inverse Compton without a sim. Yeah? In the case of Vela, we really see two components, and our colleagues of Hess were also able to put a limit. Here you see that the energy of these electrons that emit these gamma rays are enormous. Yeah. So if you consider maximum energy of the gamma rays to be around 20 TeV, you have Lorentz factors that are of 10 to the 7. An electron has a mass of 500 kilo electron volt, let's say 1 mega electron volt. So we are in regime of the 10 tera electron volt energies for the electrons. So these objects behave like natural particle accelerators. Yeah. Again, they also fitted the emission with different emission models, and they found that actually both models can more or less in different with different predictions explain roughly the emission with one of those being favored. Do you confirm what I'm saying?
It's like none of them can actually.
Yeah. Okay. which is similar to say to say that both of them can more or less do the things, but none of them can do it well. Yeah. Finally, and then I conclude. Yeah, we have a third case here. This is Geminga. It is a much older object, but it is very close as well. This is a radio quiet pulsar, the first one that was detected. It recently surged in interest again because it is embedded in a vast TeV halo, and it is even has been considered as one of the candidates for the positron excess that is measured by the AMS2 probe in the International Space Station. Although Ruben will gladly tell you about the diffusion coefficient assumptions that this conclusion depends on. Yeah, Geminga was detected by MAGIC in 2020 at a significance of around 6 sigma. Yeah, and here we had a situation that is not very different from the Vela that has measured at the lowest energies. We see a power law, actually a very steep power law, that is still compatible with the synchrocurvature emission model, but it doesn't really show any tendency of curving. So there's no indication at all that there is any curvature, which is expected if the emission is coming from curvature emission. This is also what a model, theoretical model using numerical simulations interpreted from our observations. But more recently, the LST, actually this year, also observed Geminga and confirmed the findings. It is interesting to know that the LST could detect the pulsar in less time with a higher significance than MAGIC, because it is a better telescope. Yeah, it confirmed that the existence of this power law like extension, and prefers actually a harder spectrum. Yeah, these emission models they can still, these are the gray curves in these plots. Yeah, they can still kind of explain the emission, but again here the issue is that they predict a strong curvature which we don't see. Yeah, so we really don't know if we are seeing a small inverse Compton extra component, or if it is simply the prosecution of the synchrocurvature emission. Okay, fine, I'm finished. Yeah, these pulsars, I hope I convinced you that they are extreme objects in the sense that they are extreme in itself. I barely scratched or maybe I didn't even mention the fact that they are extreme also in the fact that using Cherenkov telescopes to detect them is quite a challenge. Yeah. So all three present instruments, MAGIC, HESS, and Veritas, had pulsar programs running. But they had to do it. It was a challenge to detect these objects. Yeah, we have seen the Crab, Vela, and Geminga. The Crab is a young energetic pulsar that keeps the emission up to 1 TeV, seemingly without any jump in between. The Vela pulsar is also young and energetic, but it has this really intriguing second component that reaches 20 TeV. Geminga is older, weaker, but it also keeps up to 100 GeV without wanting to curve down. Yeah, this really produced an evolution in the theoretical frameworks. And now just to close up, 20 years ago, we only had a handful of gamma ray pulsars, then Fermi-LAT came. Now we have more than 300. We know that there is this particle acceleration that is coming from outside the magnetosphere or the wind. We have improved a lot the astrophysics understanding, but we can use, once we know how they work, these objects also to derive limits on fundamental physics. Quite interestingly, there is a pulsar timing array for the detection of the gravitational wave background in a frequency range that is not covered by the usual one, made from gamma ray Fermi-LAT pulsars. It has these advantages and disadvantages compared to the radio. Mostly the advantage is that it is not affected by the dispersion measure, the variation of the refractive index in the interstellar medium. Now, where are we now? We are at the same situation, but at the highest energies. Yeah, we only have a few pulsars around beyond few tens of GeV, but CTAO is coming. So questions are, do we have these inverse Comptons at the very high energies? Is it kind of special that we see them on some objects, or is it really that they have, for others they are very, very dim? We could, in principle, thinking of doing a multi-wavelength tomography of these objects of the magnetosphere to see, to model it in detail. With the CTAO and its improved sensitivity, we will be able also to put new limits on fundamental physics, dark matter, exotic interactions in the magnetosphere with a high magnetic field. And once we have a collection of some of these objects, we could even think on doing a study of how they evolve with the age. Yeah? So this is what I wanted to tell you. I hope I convinced you that pulsars are an interesting topic. And if you have final questions, other questions, I'm here for you. Thank you.
Thank you very much, Giovanni. The talk was excellent and you did it almost on time. So questions, I think Paula is really looking forward.
So another question, thanks for your talk. Always very clear.
Thank you.
My question is, you were showing the pulses coming from Hess, right, from Bella. So I was wondering which is the relation, because you were also saying that
This one?
yes, that the components at higher at the GeV band and TeV band looks like different, so they are coming from different emission processes. So which is the connection between these pulses and the pulses from GeV, from Fermi, for example? Any connection, no connection?
Do you mean, I mean, we know that they are in phase. This was tested by Hess. They are very much, so here they are plotted on the same plot because they come synchronous. Yeah. So they, yeah, so this is Fermi-LAT at GeV, then this is Hess, the bigger Hess, the one in the middle.
Radio?
This is radio, yeah.
Yeah, there used to be an animation, right?
It got lost in the
In the screenshot.
in the screenshotting of the presentation. So yeah, the connection is that they come in perfectly in phase, and actually this is a stringent limit because some models from the past that could hypothesize that the emission of gamma rays was in a part of the magnetosphere, but the radio came from another one. But you know that they always come in synchronous, yeah. So there is that is a huge constraint. Not necessarily, yeah? Not necessarily. So in radio you can see different things. So you see here there is also a shoulder in the middle. You can have relative motion between the pulses. In the case of crab as well, they are almost perfectly synchronous, but the precision that one gets from crab in radio is enormous. So they can calculate that there is a delay of the X component with respect to radio, and of the optical with respect to X, and gamma with respect to X, of the order, I believe it was around a few, I think it was few hundreds of microsecond. I'm not sure. Yeah. So the easiest interpretation of this is that, yeah, they are coming from slightly different regions, and then you see the delay between this. But once, if we really knew how these things worked, and then we account for these differences, if we still see those delays, then we can start to play with them. Yeah. So magic for sure. I did also Hess with Vela. I think there were studies using these pulsars on Lorentz invariance violation. So if you have the speed of light in extreme conditions is not constant on energies, then you would expect the pulses to not be in phase anymore. And yeah. And you can put limits. They did not detect any, yeah, just to be super clear, but they put limits on this phenomenon.
These pulsar timing.
It would help a lot, because if you know the intrinsic phenomenon, so what they do with pulsar timing, I was in this pulsar timing array in gamma. Let me go back to the very beginning here. So they use these ones. They use the millisecond pulsars, because these are older pulsars in which the magnetic field has decayed. So the spin down is very slow. Yeah, you see here the period derivative 10 to minus 20. Period derivative is time over time, so it's unitless. But they spin very fast. So since the period derivative is slow, they spin fast, they are old, they are almost perfect clocks. So they use these ones to do these things.
So I have more questions, but I will shut up. So
I have a question, and I have a question because I know from the hierarchy community, but I'm, working with these guys. You mentioned that before Fermi-LAT you have few pulsars, and now after Fermi came like hundreds or 300.
Yes.
What is the expectation with the CTA?
No. So
How many do we have? How many do we expect?
we have 5 right now. The expectation with the CTA, there was a paper a few years ago. I know that groups are also working currently to make updated estimates. The expectation is that we should be able to reach at least a few tens of them. Yeah.
With all 4 LSD.
With the four LSTs and the full array. Then it depends, because these estimates were made for the low energy components before we knew that the Vela-like component at 10 TeVs exist. So if we take that also into account, we might have more. Yeah.
Thank you. Other questions?
I had a curiosity. So you were saying that basically there is no big difference if you have a tilted angle between the angular momentum of the pulsar and magnetic. But what if you are actually
Opposite.
opposite?
So I say that there isn't a big difference in the phenomenon. The pulsar spins down regardless. Of course, the magnetosphere completely changes if you are tilted. This picture here, yeah, this comes from simulations. If you are on the other way around, then what happens is that you swap the charges. So here, this is the magnetic field aligned with the rotation axis. You have electrons, yes, close to the poles, and positrons here on the equator. If you do it the other way around, you are in the opposite case. So then you have the positive charges leaving from the poles and the negative ones from the equator. Interesting is that some models find that much of the particle acceleration is only on one species. So in this acceleration model where the emission is concentrated around here, if there you have positrons, it's the positrons that are accelerated, not the electrons, yeah? Vice versa, if you are in the counter-aligned.
Because whenever
case.
you are in the contra line, if you extract charges from the polar, basically means that you need to extract from the crust positive charges.
You would need to extract positive charges. This was the origin of the original in the 70s of the proposal on why there should be a polar gap at the pole. But then it was understood that the energies are so big that these can spontaneously produce pairs, so it gets filled up in that way. Yeah.
Okay, more questions? I have a very small question, but so you mentioned the bridge emission, right?
Mhm.
And I think to understand that the beams emit, it is easier, but the bridge is a bit more obscure, right? So could you describe in more detail what do you expect emission from the bridge? And also if you have a guess for the structure that you are currently seeing?
I don't. The honest answer is no, I
Because
don't.
those are still under
Different,
published data, right?
different models have really different interpretation. So in this one, you see these sets of plots are with increasing energy, but we can concentrate on the top one just to understand the thing. You have phase on the x-axis, so you're scanning phase on the x-axis. And then on the y-axis, you have your viewing angle onto the pulsar. Now, those shapes that you see there, they are the result in this model of a caustic focusing of the radiation emitted from the magnetosphere. So really, depending on where you look, the morphology can change a lot. If you go up in energy there, if you went up in colatitude, you wouldn't see one of the pulses anymore. But I know there was this model here published last year, concentrating on the emission of Vela, yeah, that was instead able to reproduce some of the features of the Vela bridge.
Those are big simulations.
Yes, yeah, the particle in cell magnetohydrodynamic simulations. Yeah. So it really depends on where you are looking and the geometry of the pulsar as well.
The structure, you don't have any guess.
No, our hope is that we are about to publish this. Yeah, our hope is that publishing data like this can really help steering the theoretical development towards making a prediction of the emission that is phase dependent, because it changes really a lot with phases. And usually theoretical models have concentrated on the averaged emission, but having a look also in the variability within the phase interval, within the rotation is interesting. Yeah.
Okay, thanks. So any final questions for Giovanni?
Let's see if there is any on Zoom.
Mhm.
I haven't been monitoring that. I don't know if there is anyone connected. No, there is no one connected.
So fine, we were all friends here. Yeah.
Okay, good.
What people connected at the beginning?
Uh-huh.
But they left.
Then they found it boring, so they left.
Very question. Okay, so let us thank Giovanni again.
Thank you.
Let's start the transmission now.
Yes. Goodbye.
And you can.
Whew.